Good morning, everyone. Thanks for being close to on time. I'm Brian Flaherty, Birch Methods Co-Director, and thanks for joining us. Gary Chan, Professor of Biostats. You can probably all read better than I, as the slide says, but also Associate Director of Birch Methods Core is going to give his third workshop on kind of causal models and inference, causal inference. And so Gary said there's some natural breakpoints throughout the presentation. And so we would maybe break for after those. And at the breakpoints, we'll pause for kind of questions. I'm going to be watching the chat. And so if you have, everybody will be muted while Gary's talking, but then we allow you to unmute during the Q&A. But if you have a question that is pressing at the moment, like clarification or something to really help the understanding in the moment, please feel free to put the question in the chat, and I'll be watching that, and I'll try to wait for a moment to interrupt Gary for the clarifying question. Anything to add, Gary, or please feel free to start.
Yeah, thank you. Thank you, Brian, for the introduction, and thanks everyone for coming. So yeah, as Brian mentioned, this is like the third short course on causal inference. So I'm going to particularly talk about models. But I guess I'll just spend maybe the first few minutes trying to go through what I have covered in the last two short courses. So the first one, by the way, they are both available on YouTube, under like the Birch website. So yeah, you can check them out if you need to. Like the first lecture was focusing on confounding adjustments, some of the most fundamental like causal inference problems, like defining counterfactual outcomes, how to estimate average treatment effects, or sometimes called marginal treatment effects. By randomization, first of all, we'll talk about how randomizations actually allow us to estimate the causal effects without the need for further adjustments. But then if we don't have a randomized trial, so if the treatment of interest is not randomized, we have to do various things. And there are basically like multiple methods. Propensity score is one. And then there's also like you can use the regression model, the usual regression model, and then do predictive margins or G computation, G formula. And also like more, I guess, recent methods that's which is related to propensity score weighting, but it's more stable in this application is covariate balance weighting. So this is what I covered in the first course. The second course I talked about treatment non-compliance. There are different sub-quantities you can estimate. The first one is intention to treat effects, which basically is just to measure just the effect of treatment assignment. But if you want to sort of estimate the efficacy, then you have to deal with non-compliance. But most of the time, non-compliance is related to unmeasured confounding. So the first lecture, the methods are all assuming confounders are all observed. So that's a problem, and you can't really just, apply things like propensity score. So we talk about principal stratification and it's related like instrumental variable methods. Like the estimates that we look at is called Ward estimates or two-stage least squares if you look at more of the econometrics literature. But then they kind of estimates the a certain treatment effects. Then So I went on to talk about mediation, defining direct indirect effects, natural versus controlled effects, different methods. For a lot of you might have heard about like Barron and Kenny type regression-based methods. But then they are based on some strong modeling assumptions. So there are some, I guess, more recent methods based on marginal structural models waiting to deal with mediation. So that was I covered in the last two short courses. And today I'm going to cover two main topics on causal models. The first one is marginal structural models, and the second is structural nested models. So if you look at the literature, you will see both, and then they have a very similar names, and so they're considerable confusion. It's actually the same person proposed these two models. So you're going to basically like see there's quite some confusion around like what are those, and then when do you use them, and then sort of the methods, and then but then I'll try to sort of mention some points of considerations. Marginal structural models are, I would say, slightly simpler, and then it's more commonly used, and then it is, and then the way to implement it is also simpler. You can sort of do regression with inverse probability weights. And then I'm going to sort of use the example, so actually a recent paper that I'm going to go over, to go through like how to estimate causal effects of PrEP for Black MSM in the US. So that's the first part. The second part would be marginal structural models. The estimation. What are those models first of all, and then how to estimate? The methods to estimate these type of models called G estimation, which is different from inverse probability weights. But then it is also connected to things that we sort of look at, in the first two short courses. And I'm going to use the example from an ongoing research about estimating the causal effects of non-surgical pain intervention with concurrent analgesic use. So yeah, so let's dive in. First of all, like as all of you, when you are in graduate school, when you take the statistics class, you will learn a lot of regression models. We will learn a lot about regression models. Right. So these are the regression models that you probably learn in different, like multiple graduate classes. Yeah, so hopefully the names are kind of familiar to you. Like there are linear regression, logistic regression, Poisson regression, Cox regression, GE, random mixed effects model. Why do we need so many different regression models? Right. So these easy answer is they are for different outcomes, right? So if you have continuous outcome, linear regression model. If you have a binary outcome, logistic regression model. If you have count outcome, Poisson. Right? If you have survival outcome, it's Cox. If you have correlated, the longitudinal or like multi-level outcomes, then use the GE or random effects, right? So they are all for sort of different situations for different outcomes. But what are they basically like? What's the essence of the models, right? So it usually specifies the functional relationship between independent variables and outcome of interest, right? And then you can include independent variables that are exposure of interest, confounders, precision variables. But those models gives you estimates, I guess categorically speaking, right? So these models gives you like association measures. And then we know association does not imply causation. So there's something missing here, or at least like, the using the regular regression model does not always gives you sort of the causal intents that you want to sort of, sort of make your scientific conclusion to. Right. So but those are useful things, right? Those are sort of fundamental things that we spend so much energy to teach them, and then you spend so much time to learn all of them. So they are all good things. So don't, I guess, throw them away, right? But one thing is like, I guess the causal model is like trying to build up from all the models that you learn from your graduate classes in order to answer causal questions. So there are some sort of good connections with the past things that you learn about, but there's also something new because, in order to answer causal questions, you have to be careful in, framing, first of all, framing a question. Second is like, you have to tweak the methods a little bit. That's what I would say. And then of course the details you're going to see it slightly later. Well, but talk about like the regression models for association. In most cases, in the simplest cases, we assume all the outcomes and predictors are completely observed. There is no missing values, right? Well, because if there's missing values, you often run into problems, right? So when missing, in practice, you do have missingness, right? So what you could do is to restrict your sample to only the complete cases. So that's a subsample, and then run a regression model on that. But so I guess we probably are being warned many times that this kind of complete case analysis is usually biased, because you are sort of taking your entire sample and then just restrict them to the complete case subsample. But your complete case subsample may not represent the whole study sample. So that's why we say that the analysis is biased, but then we could correct the bias, in other words, also like attain internal validity under various modeling assumptions and methods, such as multiple imputations, weighting, and so on. So this is from your missing data. But then causal models, what are causal models? So first of all, causal models, I guess, categorically speaking, are regression models where the dependent variable is a potential outcome or the contrast. So your dependent variables have something with, that potential outcomes appears basically. But from previous short courses, we know that the potential outcomes are actually not always observed, right? So you have, for example, you have a binary treatments, so 0, 1, right? And then you have two potential outcomes, y1, y0, right? And then y1 is only observed when someone gets the treatment. Y0 is only observed when someone gets the control. But then the y is either y1 or y0, depends on like whether you get the treatment or control, right? Then even though y is completely observed, so the factual outcome y is completely observed, but then the counterfactual outcomes are always have some missingness in it. So that's actually the fundamental problem of causal inference, which is in a way the missing data problem, right? But then because of this missing data, and the missing data happens because of treatment selection, right? Then we have to be careful. If we just do a complete case, we're going to mess up our, you know, our estimate. So that is, in a way, the reason why, causal models are different from the association models is because of this missing data problem. So just look at some examples, because simple examples, but I mean, we have to use some notations because that would kind of show you like what exactly statisticians means when we talk about like the models. So suppose we have A, which is binary outcome, X are confounders, Y parenthesis A, the counterfactual outcomes. So you have Y0 and Y1. And then Y is the factual outcomes. So the marginal structural model, the simplest one, can be written this way. So you have an expectation of a potential outcome. Now, this is a causal model because you have a potential outcome in your, as your dependent variable, right? So if your expectation of the potential outcome at different level, because A can be 0 and 1, is equals to alpha plus beta times A. Then under this model, alpha would be the expectation of Y0, and beta would be the treatment, like the average treatment effects of interest. So this can be sort of just read off from the model equation by substituting A equals to 0 and 1, right? I mean, this is similar to how you interpret your regression coefficients from like regular regression models. But the only difference, or the key difference, is that you have a counterfactual outcome, in the left-hand side of the equation. And compare this with the ordinary linear model of Y given A. So this is the ordinary linear model that used the factual outcome as the dependent variable. And again, A is the observed treatment assignment. And then, well, you have two parameters I subdenote by alpha prime, beta prime, because they are different from alpha and beta. But then from this model, this is basically just your usual linear model. So nothing fancy for this one, right? So the intercept is basically the average of your outcome for among individuals who are controls, right? And then beta is basically just the difference between the mean outcomes among the treated versus the controls, right? So this is, again, like just the usual interpretation, nothing fancy. But if confounding is present, we have shown in the first lecture that they are not the same, right? So this is the problem, right? Of course, I mean, if confounding is not present, for example, on the randomized trials, then they are the same. Like, so that's why you can use like the ordinary linear model to estimate the counterfactual model when you have randomized outcome. But if your randomized treatment, but if your treatment is not randomized, confounding is present, then you have trouble. So then you learn from epidemiology class that, oh, confounding is present, so we put confounders in the regression model, right? So this is what's exactly what you're going to do. Most of the cases, like you now have your outcome regress against the exposure and all the confounders. and then you have a model that intercepts coefficients for the treatment coefficients for the confounders. And then again, this interpretation for the coefficient of treatment is just the usual, just the usual interpretation. But then because of the no unmeasured confounding assumption, you can write this in terms of counterfactuals. Sorry. And then you can take average or marginalize both sides over x. So you average over x on both sides, which gives you, well, there's no x here, so this is the same for all x. So this is a beta double prime. And then you take average of the conditional expectation, it gives you back your average treatment effects. So in this case, like you start with a MSM marginal structural model that looks simple like this. There's no confounding, there's no x entering. This is just marginal. And then you have a regression with covariate adjustments. And then you can show that the coefficients of this regression, linear regression, is the same as the beta of the marginal structural model. So this is basically what you learn from EPI like 101, I guess. But there's a caveat, right? This requires linear assumptions for the model, and then also no A and X interactions. So if there's A and X interactions, then things get messed up. Or if you have a like log link, logit link on the left, things also get messed up. So, and then you don't really get these nice interpretations of the regression coefficients. So that's why we need to go beyond what we sort of might want to do, like with ordinary regression adjustments, when we actually want to use marginal structural model in a more general way. And marginal structural model could also be general because Y can actually be binary outcome, count outcome. So Y does not need to be, Y does not need to be actually like sort of a continuous outcome, but then you can still write the expectation of your potential outcome in this way, and then to get beta to be sort of the average treatment effect on the additive scales. Of course, you might sometimes want the treatment effect to be expressed in a different scale. We'll look at it later. So you might have a question then, like where are the confounders X in the marginal structural models, right? Because in regular regression model, you need to put confounders in order to control for, the confounding, right? But it seems kind of magic that you don't really need that in the marginal structural model. Well, the short answer is that you don't need to put confounded marginal structural model because it actually separates the modeling of the causal mechanism from everything else. So from basically the relationship of the factual models. So this is, you can think the marginal structural model is entirely, I guess, hypothetical, right? But then sometimes you also see marginal structural models that put some covariates in it. But those for situations that when you want to estimate interactions or effect modification. So suppose, say, basically like confounders, no, effect modifiers, probably. Right. So if you really just want to look at the marginal treatment effects, then you just model the marginal of mean, like the average, across your study population, right? It's the mean of the potential outcomes instead of a conditional. But if you want to, if your interest is to look at interaction or treatment effect heterogeneity, then you want to add interaction terms. For example, you can then look at marginal structural model that looks like this, right? With main effects of A, main effects of X, and the interaction terms. However, most of the time, X that defines X that are confounders, like there are a lot of X that are confounders, but then there's only a subset of X that are effect modifiers. So in those cases, say if there are only a subset of X, they call B, which are the effect modifiers of interest, then we just specified a marginal structural model, which is partially conditioned on only the effect modifiers. Right. So I guess just I guess a short conclusion from here is basically if you are not really looking at effect modifier, just use the marginal, like taking marginal over like all confounders. But then if you are interested in some effect modifiers, then put the marginal structural model also with the effect modifiers in it. But then you don't need to put all the confounders because the way to deal with confounders is next. It's completely separated from this causal modeling. Right. Well, I guess the first point is just reiterate what I just mentioned. Like the marginal structural model separates the modeling of causal parameters of interest from how the confounders are related to the outcome and treatment assignments. So that is, you think about this statement, that it basically means that, say, if you want to look at the causal effect of certain treatment, whether the treatment is randomized or self-selected, you are going to use the same marginal structural model, right? Because the causal parameter of interest are the same. Yeah. So this is basically, I think this is actually the original idea, because a lot of times we cannot compare model estimates from randomized trial and observational studies, right? Because for randomized trials, we can just look at the marginal comparison. For observational studies, in the usual way, we need to, put all confounders into a model. But then if you use a nonlinear model, then the two estimates really, like, you cannot compare. So people have a lot of hard time really, trying to sort of bridge the results, between the randomized trials and observational studies. But with the use of marginal structural models, whether you are performing a randomized trial or observational studies, they have the same parameter. And then it makes randomized trial and observational studies comparable. That's one thing, first thing nice about this. But I guess the caveat is, because I have just all talk about the model, right? I didn't really talk about like how you estimate the model parameter, right? There's no free lunch in a way, right? So although the models are the same, the model does not involve confounders, but you still need to account for confounder in the estimation phase. So that's sort of the deal here. The reason is that the counterfactual outcomes are subject to missingness even when the factual outcomes are always observed. So talk about that before, but here you see, well, I can give a marginal structural model in this way or in like a way that involves, say, effect modifier. But I don't observe all the YAs, so I can't just use at least like, yeah, I can't because I don't have YA for everyone. I don't have Y1 and I don't have Y0 for everyone, then I can't really estimate the parameters in the usual way. And in fact, like if you just do complete case analysis, basically you just use the observed, treated, observed versus observed control, then it is, basically equivalent to a regular regression of Y versus A, which is typically biased, right? So I think this is a slight dilemma, but this is like how, we want to separate the causal modeling such that the modeling does not depend on how treatment is assigned. But then when treatment is not randomly assigned, then we still need to we have to account for them in the estimation phase, because this is an estimation problem. This is actually an estimation with missing data problem. So I'll pause here for a little bit and see if there's any questions or anything that's would like me to clarify. Okay, if not, then I'll just move on. Well, the estimation, so we talk about modeling, then we talk about estimation. The estimation are quite related to the inverse probability weighting that I introduced in the first lecture. So I'm going to give a bit of a recall here, like a recap here. So say for when you have a binary A and then you want to estimate the counterfactual means, right? Mean of Y1, mean of Y0s. And then you have a propensity score, but propensity is basically a model for treatment assignments, right? This is the treatments, which is binary, and then given the probability of treatment, given the individual covariates, right? I have to answer the, so N is the sample size of your data. Then the inverse probability weighting, basically, you, first of all, fit the propensity score model, get propensity score estimates for every individual. And then you actually compute 1 over the propensity score estimates and use that as the weights. And then you, this is the inverse propensity estimator. So you sum up from the complete cases, right? So this is still A equals to 1. So this is still among the observed treated. This is still among the observed controls, right? But, you weight each of the observed treatments by the inverse of the probability that you observe, the conditional probability of observing treatment. And then you weight each observations for the control by the inverse of the probability that control is being assigned. So this is like how this is the inverse probability weighting estimator. And the reason for doing that is because it would represent the complete case subsample of treated to the combined like study population, by this inverse weight, and then it will represent the complete case sample of the controls to the entire study population. So the denominator becomes, at least like you try to represent your data to sort of the full population so that the comparisons will be, so comparisons will be based on the same underlying population. Okay. So that's the IPW. I guess a lot of you, if you have some, I guess, experience with propensity score, have seen IPW or may have used IPW. So an alternative estimator to IPW is called the hierarchy estimator, which is also sometimes called the normalized IPW. So this is very similar. It is just like instead of using 1/n, sort of average over 1/n, you sort of use as the sum of the inverse weights as the denominator. So recall like previous slides, this number is actually n, this number is actually n, but then now this hierarchy estimator actually use the sum of the weights, sum of the inverse weights within each group, right? This estimate is based on the theoretical fact that the denominators are all approximately n if the estimate of a propensity score is consistent with true propensity score. So you need to like well-fit the propensity score model. Sometimes if you have extreme weights, then in one of the groups, then maybe one of these denominators is actually much bigger than the other. And then higher estimated actually has an advantage of down weighting or well, not so to deal with your extreme weight in a certain way. So the higher estimate is actually the simplest covariate balancing estimator. It's actually balancing the balancing. I should say it's not balancing covariates, but it's balancing the constants. Right? So balancing the intercept. But anyway, so this is slightly tangential to what we need to know about MSM. But higher estimator looks like this, which is a bit strange, but it is in fact equivalent to a weighted linear regression of so the observed Y on the observed A with the inverse weights. So if you just use the observed Y regress on observed A, then I mean what you estimate is does not correspond to the marginal structural model. Right? But if you put this weights, inverse weights, then what's the least square estimator in this case has a closed form, and the closed form is exactly the same as the higher estimator. So and then as we know, then this will actually be the estimator of alpha, and then the difference between these two would be the estimator for beta. This is equivalent like what you do from the computer program. So, well, of course, like we already knew how to estimate the average treatment effect in lecture 1. So why do we need the weighted regression? So this seems to be like an overkill, but it's not because it works for general marginal structural model. Right? So far, we only use the simplest setting where A is binary to illustrate the marginal structural model. Right? But A could be continuous. A could have more levels. Right? So an A is binary because there are two groups. So the marginal mean, you only have marginal mean of y0, and you only have marginal mean of y1. Right? So you only have two quantities that you want to estimate. And the marginal structure model also have two quantities, alpha and beta. So we call this a saturated model because this is exactly putting no extra model assumptions on how, the sort of the relationship, can be constrained by the model, right? So this is called saturated model, and then it's a slightly technical work, but basically what we know is that if you have a saturated model, it's basically just, in the usual setting, it is just equivalent to doing stratification, right? So that's why you can just do stratification estimates, within A equals to 1, estimate within A equals to 0, right? Because it is a saturated model. But then if A has more than 2 level, then we still use this. Say if A has level 0, 1, 2, and then I still use this linear model that has 2 parameters, then this same as MSM is not saturated, right? When A is continuous, we always have non-saturated models, right? So we can have marginal structural model that only have increase in linearly with A. We can have marginal structural model that has some curvature, like nonlinear terms, or we can have marginal models that actually is a step function over A. So you basically can. This is our usual model building, right? We always encourage people to actually plot their data, look at like how you want to model, whether like your linear is makes sense or not, right? Doesn't always. But in all these cases, particularly when A is continuous, you don't have any saturated model. So you always have non-saturated models like this. But then you can still use weighted linear regression to estimate the parameters in any saturated or non-saturated model of marginal structural models. I think that's sort of the deal here. You can have a fancy marginal structural model, but then you can still use like a weighted linear regression. Why? So why? So say like take this as an example. Okay, so you have the linear term and the square term. Then you fit a regression model of your observed outcome, y, and then with a and a square in your independent variable, but then use the same weight. So 1 over the probability of a given x as the inverse probability weight, and then run this in your computer program. It will give you estimates of these 3 parameters. So we talk about like additive marginal structural model, but we also have multiplicative. We can also look at, let's just say, marginal structural model with different length functions. One is a multiplicative length. For example, if we want to look at causal risk ratio for a binary outcome, right? The causal risk ratios. Sorry, this is a typo. This is a probability of y1 equals to 1 divided by probability of y0 equals to 1. Right? Yeah. But the left-hand side is correct. Okay. So if we want to estimate the causal risk ratio, then the probability of interest can be expressed as a log linear MSM in this way. And then the causal risk ratio is just e to the beta. And then you can, so if your outcome is rare, then you can use a logic length function to approximate the log length function, and then you can use a weighted logistic regression to estimate the parameters. The weights are the same, basically, as before. But then the functional form is different. I think that actually makes, MSM pretty general. So you can do, generalized linear model. You can do Cox model with weights and things like that. So that's why you can think of MSM can be applied to like the different regression models that you learned from graduate schools. It's a little bit more discussion about the purpose of the inverse probability weights. So the goal is actually to create a pseudo population, I call this S, in which the marginal mean exchangeability can be attained. Okay, so marginal exchangeability is what looks like this, is that I want to estimate y1 and y0, from this pseudo population. But then I want it to be able to estimate using your observed. So then you basically want to say that you can extrapolate from the observed A to unobserved. Say if I want to estimate y0, then you use data from A equals 0, but you want to also extrapolate to the data with A equals to 1. So this is the exchangeability that is actually needed for proper causal inference. Usually, without weighting, you have to condition on confounders. Should be X. Sorry, the confounders. This has a different notations. Basically, like the usual unweighted, in the unweighted situation, exchangeability is attained only conditional on X. So that's why if you use your usual unweighted regression, you have to put in all the confounders in your model. But here, because if you use the pseudo population, then even without conditioning for the confounder, you have you have marginal exchangeability. So that's why you don't need to put confounders in your marginal structural model. This is sort of the rather technical but reason, but that's sort of ties sort of the few things together. And in the pseudo population, we can also look at the probability of assignment within the pseudo population. Actually, does not depend on confounders. So you can, in a way, these two conditions are equivalent to a randomized trial. So sometimes you will see in the epidemiology book that says that, oh, I created a pseudo population such that the treatment is randomly assigned in the pseudo population. So this is like why sometimes we will talk in this way. And then the weighted regressions also can be used for combining data from multiple studies with different population characteristics to represent a target population. So I'm going to go through this study, which is just accepted in the International Journal of Epidemiology. So, so the first author, Alison Messner, is the faculty at Fred Hutch. So, so I'm a co-author of this paper, and Alison kindly let me use some of her presentation materials in this short course. So take a look at the problem. So PrEP is, well, I guess a lot of you work in the HIV research knows a lot more than I do. Right? But PrEP is an effective intervention for HIV to reduce HIV incidence. Right? It has been studied across a variety of populations, but no randomized trials on effectiveness for black MSM in the US. But it is unethical to conduct a randomized placebo-controlled trial now or after, because FDA already approved PrEP. So yeah, I mean, it is unethical to withhold PrEP. So this, I mean, in a way, like no trials of PrEP for black MSM, partly because they didn't do a trial for black MSM before approval, and then after approval, they cannot do that. But then it's still sort of good to see how effective is PrEP, right? In this so important, population that is at HIV risk. So in order to answer this question, we need observational studies. And then in this study, we used data from two observational studies. One is the HPT, the Prevention Network, HPTN 061 study, which is a study conducted with Black MSM participants in 2009 to 2011, which is prior to FDA approval of PrEP. This study does not study PrEP, so none of the participants has PrEP access. And then we use a comparison study, HPTM 073, which is again like conducted with Black MSM participants, but right after FDA approval of PrEP. And this study is actually a study of PrEP. So all the PrEP only, basically, no control, but like everyone has PrEP access, encouraged to take PrEP, but the participants can decide whether they want to initiate, or if they initiate, whether they want to adhere to PrEP. The key question is, how can we use data from both studies to estimate the causal effect of PrEP access, initiation, adherence on HIV risk in Black MSM in the US? So a few important considerations. In both studies, we have data collected at multiple time points. A baseline, 6 months, and 12 months. And both studies are observational. And we are interested in the marginal effects to be defined later. Although both Black MSM study population, but they are slightly different. So we want to target our population to one of them, and we chose the study population of 073 because it's the trial that happens a little bit later. Okay, so here are the key variables. The exposures of interest. One is PrEP access, one is PrEP initiation, and PrEP adherence. So I denote them as ABC. And their covariates, there's baseline covariates and also covariates that change over time that we measured at 6 months. And then outcomes is HIV status that we measure at 6 and 12 months. So covariates included are listed here with expert opinions thinking these are sort of important covariates that affect HIV infection and also people willingness or to take PrEP. And we have data collection over time, 3 time periods, 0. Time T0 denotes baseline, 0 months. T1 denotes 6 months. T2 denotes 12 months. And then we have access and baseline covariates measured initially. And then we look at the initiation adherence, for 6 months, 12 months, and then time varying covariates in 6 months, and the outcomes in 6 and 12 months. Take a closer look on exposure definitions. So for the access questions, we want to ask: does the participant has access to prep? Right. When we look at data, that each study, like among 061, none of the participants have access. So A equals to 0 for everyone in 061. And then for 073, everyone has access. So everyone has A equals to 1. So in a way, this is sort of like a comparison between the two studies. And then initiation. Has the participant initiate prep at the two follow-up visits? So you have two measures. You have you have a beta, sorry, B1, B2. This is at 6 months, this is at 12 months. Because they have no assets, then there's no initiation. So in 061, everyone has B equals to 0. But then 073, then people can choose, right? They can be between 0 and 1, like B, and it can be 0 or 1. But then there's like an ordering here. If someone initiate access in B1, then they have to be continued, like B2 will be 1. Right. So if B1 is 1, then B2 will be 1. So you have this the extra constraint here. For adherence, the participant initiate prep where they adherent to prep based on the sample collected at visits, which makes 4-day adherence cutoff. So if someone does not initiate prep, then we don't need, I mean, basically, they would not meet this any of the cutoffs. So that's why C will also be 0. But then for individuals who initiated, then they may be 0 or 1. So this is sort of the nuance of like this three, I guess, exposure definitions. B and C is, in a way, it is not easy to disentangle these two because of this relationship. So instead, we define a 3-level exposure, call it D, which is 0, 1, or 2 in this way. So if they do not initiate, then D equals to 0. If they initiate but do not adhere at the visits, then D is 1. If they initiate but still adhere, then D is 2. So is actually the combined initiation and adherence exposure that we're going to use. Okay, so there are two analyses that's being done. One is the analysis on the effect of access. So the scientific question is, what is the causal effect of A, which is access or no access, on the risk of HIV infection in 1 year, which is Y2. We have this causal estimate, which, well, first of all, like they are conditional A equals to 1 because our target population is the HPTN 073, so which is A equals to 1. So we want to set this as our target, but then we want to compare people who actually get access to people who do not get access, which is the 061 participants, right? So we use the 073 data to estimate the numerator and use the 061 data to estimate the denominator, but need to we waited to represent the 073 day population. So this is the denominator is a slightly tricky. It's slightly tricky. Well, let's look at the numerator. The numerator is the easier one. So you have treatment effect among the treated. and then you also observe treatments for all of them. So you don't really need to do any, you don't need to do any weighting basically, because this is a treatment effect among the treated. So for the treated, which is the 073 participants, then the weights are 1. But then for the denominator, we need to use 061 participants, and we want to bring the 061 participant to represent the 073 study population. So we use this the weight, which basically is the ratio of the probability. Well, the reason for doing that is because probability of A equals to 0 given X is the selection probability into 061. Then if we multiply this ratio, then you are going to cancel the you're going to cancel the parts of the denominator with the with the 061 distribution, and then this will be sort of used to represent the 073 distribution. Okay, so the second question is effect on initiation and adherence. Now we basically want to look at what's the effect of D, where D is this three-factor, three-level categorical model. So we want to look at 2 versus 1 versus 0 on the risk of HIV infection. And we have data on both time points, and this is basically some sort of a causal hazard that we can define. The majority of the participants initiate PrEP in 073, right? So if we want to estimate these estimates, the denominator, you need to use the denominator for people who do not initiate PrEP, right? Since nearly 80% initiate PrEP, so you only have 20% to estimate the denominator, which makes the estimate very unstable. But what we do is, because none of the 061 people had initiated PrEP, so we pull the 073 non-initiators with the entire 061 to provide better estimates of the denominator and the whole estimate, right? But the numerators, although it is estimated from the 073 data, but we still need to reweight the observations from the observed subgroups to represent the entire 073 study population. So that's sort of the considerations. So we need to basically, well, for 061, we need to, because all of them are non-initiators. The only, thing that we need to do is to re-represent the 061 samples to the 073 samples. So we basically use the same weights. But then for the 073 sample, then we use these two weights in order to represent the subset of 073 sample who self-select into different exposure categories into the entire population. Anyway, so this is the weight, and then we use the okay. So another caveat is, because we have two time points, so that's why we use the weighted pool logistic regression. So the pool logistic regression has time-specific intercept, the common parameters for the dummy variables for the two, comparison exposures. So the first, the results shown here, this is a prep assets, which is the easier analysis. These two are the prep adherence, prep initiation, which is the slightly harder analysis. But we basically can see that, first of all, like look at prep assets. We look at risk of HIV in 1 year, and then we use the target population, often use the same target population. Then the relative risk is like less than 0.6. So the confidence interval covers 1. But you can basically see that assets alone gives you some reduction, right? But then this is not probably not the most interesting problem. You actually want to see whether PrEP actually helps. So if we actually look at these two, then it gives you a assurance that PrEP is actually doing what is intended, and then also have a very strong effect. So let's look at the comparison of PrEP adherer to people who do not initiate PrEP. Then there's over 80% decrease in risk of HIV infections. Even people who initiate but without adherence, you still have about like 55% reduction in risk. So this is some of the estimates, and this, again, like this is an illustration of how to do the sort of weighted regression in order to sort of give you more, I guess, better comparison that has causal meaning. So I'm going to pause here, see if we have any question. I guess the rest of this, well, first of all, like I finished the discussion on marginal structural models. So the rest would be on structural nested models. And that part is slightly shorter. So I want to see if anyone wants to maybe take a break, or I mean, I can do either. We take a short break or continue. I guess if there's no
Nobody's saying anything, so.
I think I would say continue.
Okay, sure. So let's continue. Okay. Well, so the other types of model, this is slightly less used because people just get confused what they are, frankly. But I actually think they are there are a lot of potentials, and these types of models, which is called structural nested models. The structural nested models is actually models that directly model causal contrasts compared to a certain baseline treatment level, conditional on observed exposures and confounders. So, well, first of all, like this model's causal contrast, so it always have to be relative to a certain baseline. So usually take A equals 0 as the baseline, and then the nested, so structural nested model looks like this, basically. Like the left-hand side is a causal contrast. So it's YA minus Y0. So it's the treatment effect. but then conditional on the covariance. So in this case, you can actually think the structural nested model is the model directly on effect modification, but without the need to model the mean or the main effect of this part. Basically, it does not estimate what is y, or it does not specify what is the expectation of y0 given a and x. It's just specify the effect of the causal contrast. So well, it might look something like this. If gamma is 0, then there's no treatment effect heterogeneity. So and we could actually test that. So it is sort of also useful for direct sort of modeling of so treatment effect heterogeneity. Because the factual y is y of a, then the model can also be written this way. This is just that there are multiple ways, and then sometimes slightly different so for structural nested type models, but then this is the one that is I guess most often used. So well, I guess so. This is sort of the model that looks like this. How do we sort of do estimation? So the method is actually called G-estimation. Again, this is another very, I guess, this gets used less because people are also quite confused about what this is. Let's take a look. So this is a family of procedure, designed for estimating the structural nested model parameters. So I use this structural nested model as illustration, right? This is the structural nested model, and then I want to estimate beta and gamma parameters. Or if we assume gamma is 0, then it's just the beta parameters, right? So what we could do is actually move this part to the left and move the part that is y0 to the right. So we just kind of rewrite the model in a way, just swap, but keep y in the left, but then move this part with your model to the left, and then to define what I call a partial outcome residual. This is not the full outcome residual because it does not minus y0. Y0 is never observed. So that's why, and then y, a, x, they are observed. So you can manipulate observed variables. You cannot, this is something you don't have, so you can't really deal with it, but you can manipulate the observed. So you define the partial outcome residual based on the observed. And here comes the magic. Okay, I should say, take this expectation condition on a and x, which will be, because the right-hand side becomes the right-hand side, which is just the thing that you don't know that you don't put it in the residual, right? So this is the part that's left out from the residual, but because of conditional mean exchangeability from non-measured confounding conditions, you actually can get rid of A. So this is the sort of, this is a deal here. So the partial residual, even though it is not a full residual, it does not have mean zero. It is independent of a given x. So this actually being used in in sort of estimation identification. So this is the partial outcome residual, and then you also define what's called the exposure or treatment residual, which is just your exposure variable minus the conditional mean, which is, in this case, it's just a propensity score, this residual has mean zero, right? Because this is what residuals is being defined. Right? The partial residual does not have mean zero because you do not know the y0. But the exposure residual has mean zero because these are just the regular residual. And then you put it both in, you multiply them, then you can show that for any function of the covariates, these kinds of quantities have mean zero, and this is actually how people can use this to construct estimating unbiased estimating equations. So in a way, this is sort of like a GE type of object. So but it is a more elaborated because it has the part that is a partial. I mean, it's not a full outcome residual, but then you use the treatment residual in order to get identification. So this is called G estimation. And because for different models, you have to, in most cases, you have to program what this thing is. So that's why there's no, I don't think there's any existing program you can use. So you have to ask a biostatistician to write program for you to do the, I guess, to estimate this kind of model. That's probably another reason why this is less used. I think for some of the linear models, it has closed forms, so it might be easier to program. But anyway, so this is what is called G estimation. It's completely different from G computation, G formula. It is for estimation of this SNM. Okay, so the structural nested models can also be written in a different scale. And we actually know that because effect modification is scale dependent, right? So you can, it really depends on your interest, whether you would like to look at linear effect modification or multiplicative effect modification. So if you want to look at multiplicative effect modification, then the multiplicative SNM looks like this. In this case, you can also define a partial outcome residual, which is y times e exponential minus this. So you basically put this to the left and then put this to the right, something like this. And then the G estimation, ideas can also be applied. Okay, so this sounds a bit too technical, but I want to sort of let you know that there are actually a lot of interesting research around this idea because people find out that structural nested model can be useful for modeling some complicated causal contrast. For example, mediation, longitudinal exposure, and also can handle unmeasured confounder. So I'm going to talk about unmeasured confounder first, and then I'm going to talk about an example that has mediation in it and unmeasured confounder. So, so recall IV methods that we discussed in the second lecture. It was formulated in I guess when I introduce in a different way, but it can also be formulated in terms of the structural nested model. Suppose we have instrument, we have exposure outcome, and then U is unmeasured confounder. Then if we consider this additive SNM, then which basically says that the unmeasured confounder does not have a effect modification with your observed with your treatment, basically. Then if you define a partial residual, we basically can show that the beta that we want from this structural mean model, structural nested model is actually the same as the Watt estimate or the two-stage least square estimate that we discussed in lecture 2. So this is sort of, a very nice illustration that, structural nested model can actually handle something, more complicated than if-out multiplication. Again, I guess maybe you will appreciate a little bit more from this example. This is an ongoing work with one of my students and with collaborators at UW. So this is actually the project that we want to disentangle sort of the effects of a certain treatment for pain, but at the same time, people are allowed to take other pain meds. So you're going to see that's other pain meds is actually going to mess up your analysis greatly. So in a randomized control trial for pain trials, the common measure of pain intensity is the 0 to 10 point numeric rating scale. So we use this as the outcome. So most non-surgical pain treatments have small, 0.5 to 0.1 NRS, mean NRS, difference. So they're sort of small effects. But at the same time, in randomized trial for those non-surgical pain treatments, as many as 80% of the patients with pain actually use the over-counter or prescribed analgesics to actually reduce pain. So you have a treatment of interest that is the non-surgical pain treatment. But people that you can control, you can randomize people to. But then what you cannot control is whether patients take, painkillers when they're in pain. So there's something sort of struggling here, because say if your treatment is effective, then your pain score will go down, right? But if your treatment is not effective, people tend to take more over-the-counter drugs, and their pain scores also go down. So if you just do a intention to treat analysis, you cannot actually disentangle the two, and then so that's why a lot of times the pain RCTs have very little effects. That is basically the big problem, right? And then the analgesic use is a post-randomized variable which acts like a mediator, right? So we cannot just do at least we have to be very careful, because it's not a baseline variable, right? So we're going to use this last trial, which is the first randomized control trial to compare the effectiveness of glucocorticoid injection versus sort of analgesic alone arm in patients with lumbar spinal stenosis. And the treatment is thought to relieve pain by reducing sort of the peripheral inflammation and ischemia. And then we have measures of post-randomization analgesic use, before the basically the measurements of the of the pain scores. But a graphical representation of the problem is we have a randomization of our treatment of interest, which is the glucocorticoid injection, right? But then after the injection, then the outcome is 3 weeks after the injection. But then in between, people can take analgesics. So, and then And then when they take analgesics, they also, I mean, that would also affect the pain score. So the problem then looks like this, where you have R, which you can randomize, but then you have a mediator, M, that's you can't really control, and you have actually might have some unmeasured sort of confounding, because it is very hard to know what happens to the people who actually get into pain and need to take the drugs. So the problem has a measured confounding, but then when you can still I guess identify or you know different pathways of interest. For example, the clinicians are actually interested in the direct effects on the studied treatment to the outcome, right? Without going through mediators. So this pathway is actually the interest. But then this is the nuisance. Okay. Well, in the absence of U, then this basically you can just do a bare uncanny estimate. That's fine. But as I say, like, you do not know what really happens to people before they take the analgesics. What caused the pain? What caused the sudden pain, for example, right? And then I'm just sort of this is basically just to illustrate that this is different from the usual mediation setting, and also if you don't have the direct effect, this looks like instrumental variable, but this is also not instrumental variable setting. So this is a setting that is less, it's less studied. So if we define counterfactual variables, y r of m, where R is the treatment of interest, M is the analgesic use, then we actually can have a potential pain score in this way. And because analgesic use also post-treatment, so we have a potential analgesic use variable. And the usual consistency is that the factual outcome is just a counterfactual outcome when with the observed variables. So we assume randomization and also like the unmeasured confounding will attain exchangeability, and we use this structural nested model, for analysis. If I look at what this is, basically it compares the observed y or y of R and M basically to y00. So when you do not have when you do not have well, basically like in the control group, and also do not use analgesics. If it looks like this, and there is in order to explain the I guess interpret the coefficients actually does have the interpretation as you see in the causal diagram. So theta R0 is actually the direct effect of R to M, R to Y, and then this is the effect of M to Y. So if we use this additive structural nested model and some kind of G estimation, again, like this is not the usual SNM, so we actually have to tweak the G estimation in different ways to make this work. That is my students' project, basically. But I want to kind of show you the comparison of results here. So if you look at the intention to treat analysis, you have an estimate this is like the treatment has like a decrease the pain score by 0.67, right? But then it is likely to be attenuated because of the differential use of analgesics. So if we do, but the regression is basically just like Barron and Kenny assuming that the confounders, there's no unmeasured confounder. When you do this, it doesn't really help with the estimates. And then this estimate is the theta m, is the effects of m to y. This estimate actually has the wrong sign because it says that if you use painkiller, you will have more pain, right? Well, even though this is like a small number and non-significant, but this is of the wrong sign. This is potentially due to a measured confounder. So that's why this is sort of the first place why we want to deal with a measured confounder. And then if we use this SNM, we will get an estimate that is, I guess, is more reasonable in a way that it is, larger than the ITT, as expected, because there's less attenuation if we sort of properly take an account of the analgesic use. And also the analgesic use also is, have a reasonable estimates. In some other trials, the analgesic use estimate is around negative 1.5. Basically saying that like if people use analgesics, they'll have a 1.5 point decrease in pain score, right? This is close, and so also like this estimate is also more reasonable, at least without the attenuation of the differential analgesic use. So this is sort of an illustration, that a nested, structured nested model can deal with this situation. You cannot use marginal structural model because marginal structural model cannot handle unmeasured confounding. Yeah, I think, I mean, if everything equal, structural nested model seems to be less useful if you can. I mean, you don't have this unmeasured confounding issues, but actually a lot of times when you have mediation or time varying problems, you do have a lot of situations that you actually want some protection from unmeasured confounding. So that's why I find like SNM is at least from myself, I have students actively working on this directions. Okay, so I guess I'll provide a summary of what I have covered so far. So there are two classes of causal models. They generalize methods for simple settings. The simple settings are the ones that we have already looked at in the past two short courses. So then these are the two large classes. One is marginal structural models. The nice thing about it is it separates counterfactual modeling from that of full outcome modeling or treatment assignments. And then you correct the bias of the unweighted analysis by weighting in which a pseudo population is created that attains marginal exchangeability. And then the marginal exchangeability allows you to separately model the counterfactual. So that's sort of a nice sort of combination. Structural nested models, on the other hand, are model that model contrast but not the main effects. It is useful when you when the contrast is much simpler than than mixed effect. Actually, I do have another example from one of my ongoing PhD student, is that we actually want to look at like the optimal treatment regime. Right? The optimal treatment regime, some people use marginal structural model, but then the marginal structural model has a very ugly, or maybe the main effects actually very complicated. But sometimes the main effect is complicated. Maybe main effect depends on a lot of confounders, but then the heterogeneity actually only depends on very few variables, and it's much simpler. So in this case, actually, like structural nested models also is very useful. But then the estimation by G, like the G estimation, is basically estimating equation-based methods constructed by partial outcome residual and then like a treatment residual. But then these kinds of things, because you have to use a different partial residual, outcome residual, and different treatment residuals, so it is, but at least like it is less available to analysts. So we at least like we have to program it every time we use it, but it has the your added advantage to handle unmeasured confounder thing under certain assumptions. So yeah, so I guess that's all for my the lecture today, and I'm happy to take questions.
Thank you for the presentation. This is probably my first exposure to causal models, so and I haven't attended the previous lectures, so I'll definitely go and check them. One sort of big picture question. So I'm trained and I've been exposed very much to the ordinary model or the models for associations as you described them. Mm-hmm. So if I am analyzing data from a trial, which the objective of the trial would be to assess causation, right? So and for example, I have a problem with unmeasured confounding. Does that in of itself negate or disqualify the other models, the basic models that I'm trained on, and then I'll have to definitely use one of the causal models, MSM or SNM?
Yeah, thanks for your question. But I guess maybe I would like to ask a little bit of clarification. So say suppose you have a trial, then if is your treatment randomized?
Yes.
So yeah, if your treatment is randomized, then you actually can but first of all, like if your treatment is randomized, and then of course you might have like a treatment non-adherence, those kinds of things, right? So but if you're just I guess the first thing that people usually do, because you have something randomized, you can take advantage of the randomization, and then you can do something simple. Without doing this model, people will just do an intent to treat because it does not require. But yeah, it in a way it is just more like a say difference in mean. You can do a t-test and things like that. So without going into the details, you can like the first analysis, or probably the primary analysis usually people do would be intention to treat. But after intention to treat, sometimes people would actually want to understand the causal mechanisms a little bit more. Then this is when the causal models comes. Actually, if I look at this, this is actually from a trial. The data is from a trial. This is randomized, but then this is not randomized. Then it is not the same as non-compliance, but it is similar because people can. But non-compliance is usually say I randomize to a drug, but then people do not take the same drug. now this is like I randomized to an intervention, people take another intervention that I don't have control. So there are some like similarities, but also difference in this case. But intention to treat is okay, because intention to treat, you can think you are actually estimating R to Y without considering whatever happens in between. So
Yeah.
that is the intention to treat that is here.
Mhm.
Right.
Mhm.
So it is actually like, you know, the main results, the trial's main results is actually published in New England Journal of Medicine. So it has this kinds of intention to treat effect. Right. But then people then think about, you know, intention to treat may have limitations. Say in this case is the, you know, the other, because the control may actually we actually see the control people take the painkiller more. So that's why we think, okay, intention to treat is attenuated. So if you want to get a more I guess a better sense of, I guess, removing the effect of the analgesics, what would happen, then you use this causal model. So I think it is usually a secondary question, uh, but also requires more thinking, more modeling. So I guess it depends on the, I mean,
Yeah.
usually the primary goal of the trial intention trees is good enough. But then follow-up work, people might want to sort of look at these kinds of things. Does
Just a
that
quick
make sense?
follow-up. Yes,
Yes.
yes, a quick follow-up, and I don't wanna leave room for others to ask questions. So this is probably the first time I hear the distinction between ITT and regression. So I need to go back and understand it better. But maybe is it, or is there a reason why someone would analyze data using regression versus ITT?
Yeah. Okay. So yeah, this is probably here.
Yeah.
Yeah. Yeah. So sorry, I actually didn't explain this too well. So ITTs can also be formulated in terms of regression. So I should, but so if you just have Y, your outcome, and then regress on your treatment, in this case, I call it R, then it is ITT. Yeah. Here the regression, I should actually make it more specific. I actually add but so here I only have R, so it is ITT. But this regression model, I have R and also M in the regression model. So I actually take the mediator in the regression model. This is actually something that people sometimes warn against doing because M is a post-treatment variable. But this is also like sometimes people would do in this case. So
Yes.
that's why I put it here for comparison.
Okay, thank you so much.
Yeah, you're welcome.
Thanks everyone for joining us.